So I'm Shen. Oh, you can see both. No. You can see the. Sure. We need to stop. Okay. And share the file. Share this. No, it's better to share the screen. Share the screen. Screen this monitor. Okay. No, I think we need to share this. Oh, then look, unplug. Look. No. No, but if you plug this one, we'll share this one if you want. But you can share the duplicate. Yes. Share this screen. Oh. Yes. Then drag down the yes. Okay, so can you all see the screen now? So this actually the second lecture that we're going to deliver. So good afternoon once again to Prof. Kim and the students. I'm Shen from Hocklim Engineering, continuing our industry collaboration with SIT and the University of Glasgow. So today's topic is on coordinates and traversing. So it may sound very mathematical, but it's actually one of the most practical tools that you need to use in construction. I think whether you are checking a slope instrument's position or locating a drainage culvert accurately within a built-up space, understanding coordinates ensures that every point on site actually matches the design model. So this section is going to build upon what we learned earlier on the angles, synthesis, and leveling. So I hope you haven't forgotten about that. So we'll go through systems, how we represent positions on Earth, and traversing, which later page how we'll go through, how to build and maintain site control. So just want to touch upon these two concepts. They are actually what make digital engineering possible, from things like from your GNSS receivers to your total station traversing. And all this will be able to ensure that your slope or drain can be built exactly where it should be. So this slide, we are going to introduce the Singapore coordinate system called SVY21. So in Singapore, we use this SVY21 coordinate system, and this is actually developed by SLA for consistent mapping across the island. So why does this matter to us in the field? Because when we construct a new drain, all our coordinates tie back to the national control points. This actually helps us to layer our data with PUB and similarly other agencies' data sets accurately. So for example, let's say we are designing a cross drain across Bukit Timah Road. We use the SVY21 coordinates to ensure that the outlet matches the downstream catchment model, and it also coordinates well with LTA's road reserve lines and even the landed properties boundary lines. So this is why the coordinate system is important. And what is this level surface? So horizontal plane is a level surface, and a horizontal plane is level in simple surveying, but in geodetic terms, a level surface actually curves with the earth. So I think you will ask why is this important? So in a very large slope site, say a 1 kilometer hillside near Mandai area, assuming that the Earth is flat actually introduces a lot of errors when you start to compute your control points. So in short, I think plane surveying works for small projects, but for nationwide or long linear works such as like canals or expressway, we have to adopt geodetic corrections. And so we talk about the shape of the Earth. So the Earth is actually not a perfect sphere. Actually, it bounces a little bit at the equator, and that's why we have to use mathematical surfaces to approximate this bulge. We use the ellipsoid and the geoid, which is the words in blue you see. So I want you to think of the ellipsoid as somewhat of a mathematical egg, well, while the geoid actually follows the mean sea level. So the mean sea level for surveying terms, they always use it as a MSL, and it's where the surface of the water will settle. So for Singapore's low-lying drainage systems, this distinction is actually key. So our vertical datum actually ties directly to the MSL. So when you say that it's 0.00 meters a reduced level, you go to another project site and you say 0.00 meters reduced level, you will get the same level. So ellipsoids actually help to provide a global reference for mapping. In Singapore, we're right on the equator, right? So we need to choose something that matches our local shape. So I think basically in Singapore, we use this thing called a WGS84. And then similarly, it's get tied back to the SVI21. And this is designed to match the local curvature. And I think what you need to take note of is when you start to import in your GNSS coordinates into your CAD model, if you use the wrong projection or use the wrong ellipsoid, your CAD drawing or your alignment can actually end up 1 or 2 meters off the plan, even though everything is the same. It's just the mathematical model that is used to put into your CAD model. So that's why it's important to always confirm your datum and your projection before you start to integrate your field data into your model. Okay, so the geoid actually represents the mean sea level across the Earth. And what we are normally referring to is this thing called the zero height surface. So in Singapore, our reference is actually the Singapore height datum, the SHD, and they have a lot of zeros behind, so just 0.000 meters. So it corresponds to the mean sea level at Keppel Harbour. So when we do leveling for drainage design, every invert level or manhole cover height must be referenced to this SHD. And because everything is referenced to the SHD, we can check things like the gradient and whether the water flows correctly from upstream to downstream, whether the drainage makes sense or not. And I think what is important to note is that even something like a 5 millimeter mismatch between two surveyors' datum. So you have a surveyor A and surveyor B, and they do survey, and they're supposed to meet somewhere in the middle. And if there's this error, actually it can cause ponding or even backflow in some cases. And that's why good geoid models matter a lot. So I'm going to dive into geoid heights. If you see the thick black line on top, which is topography. You see the ellipsoid at the bottom, and you see a geoid model, and you see a true geoid. So I think from here, what I'm trying to say is that you very often see this equation, capital H equals to small h plus big N. And if you refer to it, it's actually adding this to, we can't see also, let me see. It's actually adding, yeah, so like in this case, for point H in a topography, you really have to add both the autometric height and this separation to get your geoid model. So when we discuss this topic on geoid height, basically we are talking about the error measurements for in this case the HA and the HB. And when you start to compare the difference, you can actually remove some of these errors by differencing. Maybe something that is more applicable to this. So actually in practice, when we use the GNSS to check a slope crest, we put it on the slope and we press to get a reading. The GPS actually give us the ellipsoidal height, which is the one at the bottom. Yeah, this is what you get from a GNSS reading. So we select the correct geoid model, and then we get this height. So then after it plugs together, you get the topography. But I think basically what we're trying to do is we're trying to get you to understand that there are errors in the calculations and that your GNSS output cannot be directly used in your calculations. So you need to account for this geoid height as well. So if you don't apply this correction, actually your data will start to drift, especially when you start to combine between different systems. Like you have the traditional surveying total station level, and then you try to combine with your GNS data, and then you realize that there's some mismatch that's very difficult to meet or to resolve. So one of it could be your geoid height. Okay, so we talk about the mean sea level height. So the Singapore height datum basically is the vertical datum at 0.000 meters. This is introduced by SLA in 2015. And the SHD basically unifies all the agencies under one vertical reference. So actually, prior to the SHD, some contractors use site 0.00 and local vertical height datums. So it can cause a lot of confusion and actually a lot of mismatch when they start to when they attempt to merge two plans together. So today, thanks to this Singapore Height Datum establishment, every drainage project submitted to the PUB must be referenced to the SHD, and in your future work, always confirm that the benchmark reduced level. Don't assume that it equals to the sea level. So even when we say the reduced level is like a 0.00, you always need to check whether is it referring to the Singapore height datum or not. I think this is one of the most common rookie mistakes. Okay, so there are a couple of coordinate systems out there. I think there's three that we'll go through. So the first one, system number one, is on the latitude, longitude, and ellipsoidal height. So latitude and longitude basically locate positions globally. I think what is easy to understand from latitude and longitude is that when you click on Google Maps, actually the coordinates on Google Maps are in lat and long. So when you talk about like slope monitoring, actually we need to transform the lat and long coordinates back into SVY21, which is the Singapore coordinate system that we talked about earlier, so that they can be aligned to the Singapore's mapping grid. So remember previously we were talking about curvature of the Earth, bulging at the equator, and stuff like that. So even when Google gives you a lat long coordinate, when you start to transfer it back onto the Singapore's grid, there are some what we call like conversion errors. So I think it's important to take note how this coordinate system relates back to SVI21. So I think back to the GPS instruments. So when they record down latitude and longitude, it's the surveyor's job to convert and check that this derived easting and northing actually fits your coordinates framework. So if you install something like an inclinometer on the slope and your GNSS readings come to you in latitude and longitude, make sure to convert them before plotting them on your plan. Okay, there's another system called the Cartesian coordinates. These are in X, Y, and Z. So previously, those are like pretty like the two-dimensional. I think for this one, they actually incorporate the Z in it. So they are basically mainly used in computational works, especially when you're trying to integrate GNSS with total station. So you adopt a particular coordinate to suit your use case. So in this case, the Cartesian coordinates rely on how the x-axis passes through the prime meridian and how the y-axis also passes through the meridian 90-degree east. And through this kind of mathematical concepts, you can sort of link the GNSS and total station traditional surveying methods together. So the third coordinate system is the easting and northings. So easting and northing is already compressed onto a 2D plane, and eastings is normally called X, and northings is normally called Y, and they form this 2D grid of the curved surface of the Earth. And actually, these are the coordinates that we use day to day on site. So when we perform like traversing on a slope, we compute easting and northings for each control point so that the total stations can reference them easily. I think what we are basically trying to get the students to understand is that we are trying to separate the height, measuring the heights and plotting them on the X and Y plane. So I think one project that we recently completed is at the Furama slope. We actually established 4 control points around the hill, and then each of them are tied to the SVI21 easting and northings. So this helped us to align the slope, set out our drain lines accurately, and at the same time, we use the coordinates to monitor movement of the slope during and after construction. Okay, so I've been talking a lot about GNSS in the earlier slides. So there's this service. It's called the IGS, International GNSS Service. So I want to reference for all of you that use GPS, maybe on a daily basis. I say that you're driving or you use your Google Maps, for example, and you will know that the GPS actually comes from your satellite data. And from your satellite data, they do some triangulation in the outer space, and when it comes down back to you, they can get your position accurately. So you also know that because it is up in outer space, actually, if there's a lot of clouds on that day, then it actually takes longer to reference your point. And this becomes more acute when you're carrying out surveying work, because you are the one that's going to be doing the triangulation. So you will need to know what are the data points out there and how accurate is it. I think a little bit more about this Singapore Satellite Positioning Reference Network, SIREN. So most of most of our RTK, this real-time kinematics comes from siren, and actually they let's say you want to set up some long drainage or you're trying to monitor some slope deformation, we need to connect our GPS receivers to the siren's RTK network. So of course, being a service, there are a lot of charges coming to it. So it goes by like level of accuracy and how many of these GPS receivers do you need. If you want it to triangulate this data back down and you have a few points, then it'll be more, you need more stations and it'll cost more expensive. So once you have this siren on your side, it actually corrects for atmospheric and orbital errors, which is what you get when you're working with the satellites. And this will actually give us very accurate and survey grade kind of precision on the ground. So I think this is one of the ways that Singapore's infrastructure actually helps to push this surveying accuracy up one more notch. Yeah. Okay, rectangular coordinates. So the best practice for this rectangular coordinates, basically you're trying to make some kind of local coordinate system. You should always define your north axis and ensure that all your coordinates are positive. Positive, it means top and right. Yeah, so you try to keep your origin in this orientation, try to put it in the north and try to make all your coordinates positive so that it's easy to do your arithmetic work. So I think basically it helps to keep all your computation straightforward, and it also prevents some confusion, especially when you're trying to migrate this local coordinate system onto AutoCAD. Yeah, so I think it's good to take note of that. Okay, a bit more about the polar coordinates. So this is actually trigonometry. You need to be quite familiar with how to derive your angles, and maybe I can discuss surveying actually allows us to express your position, where you are, your x and y, where you are in either a rectangular, which is the before that, the northing and eastings, or in a polar kind of coordinate. Polar means you give distance and bearing. Bearing is in degrees and distance is in meters. So on sites, actually your total station, when they give you the display, they give it to you in polar values. So they give you an angle and a distance. And then because total stations are so advanced now, they can compute the northing and eastings automatically. So I think you'll be exposed to that in the field, converting polar coordinates into easting and northing. I think what they give, what the slides talk about now is on an example. So I will go through the example with you. So say you are at A, and it's given that you are given like a easting and a northing as above. After charting out your distance and your bearing, which is like 57 meters and about 67 degrees, you actually are supposed to find what is point B in northing and eastings. So basically they resolve it using your inverse sine, and over here you use your inverse cosine. I'm not sure whether the secondary schools curriculum is still the same, but we used to say like the tangent is like opposite over adjacent, and like sine is like opposite over hypotenuse and stuff like that. So so I think from that we are getting you to do it manually and to do the computation manually, and even though the total station can do it internally, but understanding this mathematics actually helps you to verify the result. So similarly, if given some coordinates, you can also understand what is the polar coordinates. So I think in this work example, we give the northing and eastings for A and B, and basically we are told to calculate the distance and the bearing between them. So from here, actually, they give the point A, they give the point B. You need to calculate your difference in easting, your difference in northing, and then from there, you can use a simple trigonometry to calculate the distance and of course the bearing. I think it's important to take note for the bearing because you have already aligned it to the north. You need to make sure to plus the 90-degree here. Yeah. So I think what's important is you need to cross-check your computed values against your field measurements so that you can catch your errors early and stop it from going down and carrying the error forward. Okay, so my colleague Pei Cao will be going through the next segment with you. Thank you.
Okay, good afternoon, everyone. Happy to see you again online. I hope you are still awake after lunch, right? Because this lecture is really important, although a little bit difficult to understand. Like what Shen has already explained and introduced, quite some important concepts you need to understand. And after that, I'm going to introduce more concepts and also ideas. I mean, methods also. The one important thing is traversing. All right, so let's shift our gear a little. I'm going to show you how we actually connect the points on the Earth together in the field. All right, through something we call traverse. So traverse is basically a network of survey lines that join a series of control points together. You can think of it as a skeleton of the site. Once we have this framework, we can map everything else and more importantly, set up where new structures will be built. For example, on a drainage construction site, before we start excavation or install any box culvert, we must establish a control traverse along the drain alignment. Each bend, each stump, and each change of gradient, all these are referenced from the traverse. So in practice, every site survey should start from traversing. Okay, now a control network, or we call control traverse, is simply a group of these control points. Those positions and height are accurately known. All right, these are the anchors of your entire project. Everything you measure or set up later, the levels, the distance, boundaries, all rely on the accuracy of these points. So every construction site, from a small drainage upgrading project to a major slot protection project, will have its own control network. For example, when we are working on a slot repair project along an expressway, we often have to set up control points at both the top and the toe of the slot. The top points control the alignment of the drainage channel and the guardrails, while the bottom ones help us to set up the retaining wall alignment and the V-posts. And the horizontal control will be exercised using a coordinate system, usually with a rectangular coordinates, which that will be covered later. The vertical or height control is maintained by leveling, which we have covered in the last lecture, or by trigonometric height from the total station. So only on construction sites to a great extent that does plane surveying become invalid, in which case the projection and the evaluation scale factors must be used. Okay, so how do we establish new points once we have a few known ones? That's where traversing comes in. We start from a known control point, say a benchmark near the circuit, right? And we walk the traverse across the site, measuring the distance and the angles between the stations using a total station. Each point's coordinates are computed from the previous one using the formulas that Shen has covered earlier, like delta E equals to distance times sine theta, and delta N equals to D times cosine theta. All right. I'll slow down here when we go into calculation later. But the key idea now is that traversing allows us to extend our control network safely and accurately. In a drainage project, for example, we might establish new points along the proposed drain alignment so that your as-built and the design coordinates always match each other on the site control system. Okay, now let's talk about where traversing shows up in the real life. We use it for three major purposes. The first one is mapping existing features, like when you do topographic graphic survey. Before the construction starts, we use a traverse to locate existing manholes, trees, curbs, structures, and boundaries. All right. For example, when upgrading a roadside drain, we will traverse along the road and capture all the existing inlets and outlets positions, whatever curb, existing drain, side boundaries, adjacent structures, sewer manhole, water pipe, fire hydrants, or even the lamp posts. So all this will be captured by this traversing. That's what we call mapping existing features. Okay, another application is setting up new construction. Once the design is approved, we use the same traverse points to set up the new like in center line or the building position, and the vital line of a slope, or the exact position of some retaining structures. This ensures that what we build matches the coordinates on the design drawings. The third application is checking the completed work. So after construction, traverses help in as-built survey. Then we can compare the coordinates of the constructed points with the design coordinates to verify compliance. This is something that every LTA or PUB inspector loves to see. Let me give you a quick example. On one of our drainage project in Admiralty Road West, we had a box culvert running about 70 meters across the road. And we set up a closed traverse around the site before excavation. But midway through, one of the control packs got disturbed by machinery. But luckily, because we had a closed traverse, we could easily re-establish that point using the rest of the network. That's the beauty of a proper traverse. It gives you redundancy and the confidence. So in summary, traverses are like the backbone of your site coordinate system. They connect known control points, help you extend the network and the support every stage, from mapping to setting out to as-built verification. In the next section, we will dive into the calculations behind traverses, how to handle bearings, angular misclosures, and the coordinate adjustment, which are the real bolts and nuts of surveying accuracy. Okay, now to perform traverse calculations, we first need to understand bearings, especially whole circle bearings or WCBs. So in simple terms, a bearing tells us the direction of one point from another. And the whole circle bearing is always measured clockwise, all right, from the north axis. Repeat, whole circle bearing is always measured clockwise from the north. This is very important. Remember, if you don't remember and don't understand this, later on you will always get confusion when you compute your bearing. Okay? So you just imagine it's just like a compass that goes from 0 to 360 degrees. All right, clockwise. So if a line point due east is 90 degree and due south is 180 degree. Okay, and if a due west is 270 degree and back to north is 360 degree, or we reset again as 0 degree. So you can think of it like turning your total station horizontally. One full rotation gives you the full circle bearing. Why do we need this? Because in traversing, we use bearing to compute the direction of each line and then break it down into the easting and the northing components. Okay, let's look at this diagram. We have two lines, all right, RS and the ST. And each line has a forward bearing. That's the direction you measure as you move forward along the traverse. And they also have a bearing, which is simply the reverse direction. All right. So now let's look at the forward bearing first. If the forward bearing from R to S is 120 degree, so this 120 degree again, I repeat, it starts from north axis, goes to this line RS, you can measure 120 degree. All right. So then this is what we call forward bearing. So this forward bearing from R to S is 120 degree. Then the bearing from S back to R is what? Is 120 degree first, because here is 120 degree. You transfer this 120 degree back to S, then you get the same 120 degree if you extend this RS a bit longer. So you have a 120 degree here, right? And then you rotate another 180 degree, then you can get your back bearing from S to R, which is 300 degree. Okay, I hope you understand now. Should be easy, right? 130 degree plus 180 degree, you get your back bearing. So here, it's simple as that. Your back bearing is your front bearing plus or minus 180 degree. If your forward bearing is less than 180 degree, you plus 180 degree. If your forward bearing is more than 180 degree, then you minus 180 degree. Okay, simple. If your calculator gives you something above 360 degree, you don't panic. Just subtract 360 degree, and you'll be back into the proper range. So this small detail is crucial in the field. When you set up drainage alignment or your boundary, you often work in both directions. For example, one team may traverse at the downstream of the drain, and another at the upstream. So if your bearing are flipped, then your drain will laterally flow in the wrong direction on paper. Okay, so really need to be careful. Okay, here is another example of forward and back bearing. The forward bearing is this is A. Okay, A, B, C, D. All right. So they told you that the forward bearing for AB is 31 degree, for BC is 157 degree 30 minute. For CD is 200 degree, and for DA is 347 degree 15 minute. Okay, so by using the method I explained just now in the previous slide, you can calculate the back bearing, which is BA, CB, DC, and AD. All right. So how do you do? Just plus minus 180 degree. So from 31 degree, you plus 180 degree, you can get 211 degree. 157 degree 30 minutes, you plus 180 degree, you get 337 degree 30 seconds. So on and so forth. For the last one, for the last two, if you add, okay, 200 is more than 180, so you minus 180 degree, you get 20 degree. Same thing for 347 degree 15 minute, you minus 180 degree, you get 167 degree 15 seconds. Okay. So now we've covered bearing. Let's talk about types of traverses. There are two main types of traverses you will see on site. One is link or connecting traverses, and another one is called closed traverses. So this slide showing a link traverse. So in a link traverse, the line connect between two known points. Okay, for example, AB, right? From an existing benchmark near, let's say, a road junction to another known station near a canal. So we use this when extending control from one side to another. But in most construction sites, especially for building projects, we use a closed traverse, which is a form a loop, and that's where it begins. Okay, this is extremely useful because it allow us to check the accuracy. So if we return to the same starting point, any small measurement errors become visible. Okay. So now let's take this example of a closed traverse with 6 points, A, B, C, D, E, and F. Okay. So we will use this to illustrate the calculation process of traversing. So how do we determine the coordinates of each station? We check for so actually we use this calculation to determine the coordinates of each station, and also check for the angular misclosure and adjust the calculated data if necessary. So think of it as setting up control points around the building construction site. Okay, maybe A is near the entrance, and B and C follow along the boundary alignment, and the D to F loop around the work area before coming back to A. Okay, so by closing the loop, we can check both angle and distance accuracy. It is a critical step before you start any actual work on site. Okay, so here are 5 steps to do the closed traverse calculation. First step is check the angular misclosure. Secondly, calculate the whole circle bearings. And thirdly, calculate the coordinate difference and the misclosure. And fourthly, assess accuracy and apply adjustment. Finally, calculate the coordinates of traverse stations. So like what Shen mentioned just now, you don't go until the end, you find a big error, but step by step, you correct the errors, right? So that's where the 5 steps comes out. Okay. So step 1, check the angular misclosure. So when we measure the internal angles of a closed traverse, the total should theoretically equal to 2n minus 4 times 90 degree, or to make it simple, n minus 2 times 180 degree, where n is the number of the sides or angles inside the closed traverse. All right. Of course, that's for internal angles. And for external angles, is 2n plus 4 times 90 degree, or n plus 2 times 180 degree. Okay. In real life, because of instrument precision, or site errors, or human fatigue, we always get a small difference. That's called the angle misclosure. So what do? We can simply distribute that small error evenly among all the measured angles. Of course, before we distribute the errors, we need to check if the errors is small enough to be accepted. So how can we know that whether it is small enough? Here is rule of thumb. Okay, the allowable error of this angular misclosure is given by E equals to plus minus K times S times square root of N, where K varies from 1 to 3, depends on the weather condition or the number of rounds taken, how many power points, how long, how far I go, okay? And S is the smallest reading interval in seconds of your total station or your instrument. So if the angles of the closed traverse consider were measured using a 10-second instrument. So the when K equals to 1, the acceptable error is plus minus 1 times 10 seconds, which is S, times 6, which is the number of angles, right? Just on the previous sketch, square root of 6, you get 24 seconds. And when K equals to 3, due to some bad weather or very long distance you travel, the acceptable error can be 3 plus minus 3 times 10 seconds times square root of 6. Then you get 22 seconds. So if the misclosure is acceptable, it is distributed evenly around the angle, like what I say. But if not acceptable, let's say, we have an 80-second error, which is more than 72, then sorry, you have to go back to your site and do the angle measurement again. Then you check until the error is acceptable. Okay, for example, if our traverse have these 6 sides or angles, right? The misclosure is plus 60 seconds. After we calculated the allowable error just now, let's say if the allowable is 72 seconds, then okay, roughly we can accept this 60 seconds as the error. Then we can distribute these 60 seconds evenly to each point or each angle. All right, we just subtract 10 seconds from each internal angle to balance it out. It's just like when you are installing drain, if your alignment is 60 mm off over the whole length, you don't shift the last point by 60 mm, but you correct each segment slightly, like 10 mm, 20 mm, 30 mm. Then at the end, you can finally get your line up perfectly. All right, so it's the same concept. Okay, so after adjusting the angles, we move to step 2, calculating the bearings. So here some definitions are required. First is this left-hand angle. All right, what is left-hand angle? Is the internal angle when traveling anti-clockwise. The external angle when you travel clockwise, for anti-clockwise travel. The forward bearing, which is like bearing FA and AB, okay? And the back bearing becomes BA or AF. So in general, for any traverse station, the forward bearing equals to back bearing plus left hand angle. All right, so this is another way to calculate your WCB. Previously, I mentioned that you use forward bearing plus your plus or minus 180 degree, you can get the back bearing. So this is another method. Forward bearing equals to back bearing plus left hand angle. Okay. So the calculation of WCB must start with a known bearing, or at least you assume that you know this bearing. Okay, must be known the first point. Okay, so you start with a known or assumed bearing for the first line. Let's say the line AB, okay, has a forward bearing of 185 degree, 11 minute, and 10 second. How you get this? Is from the 70 degree from the north, all right, and plus the inner angle, or we call it adjusted left hand angle A, right, which is 150 degree, 11 minute. Here you say 20 seconds, right? This is unadjusted. After adjustment is actually 10 seconds. So you add up together, you can get 185 degree, 11 minute, and 10 seconds. Okay. Then at the station B, okay, we can find the back bearing from this point B, or we call it BA, simply by adding or subtracting 180 degree. So in this example, is 150 degree, 11 minute, 10 second, plus or minus plus minus 180 degree. So you get either 365 degree or 5 degree. Okay, but eventually this 165 you need to minus 360. So eventually you get this 5 degree, 11 minute, and 10 second. And so forward bearing BC, okay, is here is 5 degree, right? 5 degree, 11 minute, and 10 second. Plus here, the adjusted left hand angle, which is 95 degree. Then you get 100 degree, 11 minute, 10 second. Okay, that's what the sketch shows. So you just repeat the procedure, then you can get back bearing CB, then forward bearing CD. Okay, how do we do that? Come to the next slide. At station C, all right, the forward bearing CD equals to the back bearing CB plus angle C. This angle C is the adjusted left hand angle. Okay, back bearing of CB is obtained from the forward bearing of BC, which we calculated 100 degree, 11 minute, second in the previous slide, right? Back bearing, how to do? Plus or minus 180 degree. Then you get this 280 degree, 11 minute, second. And after that, you plus this angle again, which is 129 degree, 49 minute, 10 second. Okay, then you of course this angle is unadjusted yet. So after adjustment is 129 degree, 49 minute, no second. Okay, so add up together, you get 410 degree, 10 second. So it's more than 360 degree. You need to minus 360 degree. Then you get 50 degree, 10 second. I hope everybody following until now. so far this is the most important procedures for you to calculate the bearings, forward and backwards. Okay, so must understand. Okay, so this step-by-step addition continues around the whole traverse until we return to the first line, which is AB. All right. At the end, you need to check the WCB calculations. If at some stage in the calculation a forward bearing is greater than 360 degree, then you just simply subtract 360 degree to obtain the correct bearing. And the last lines forward bearing should differ by exactly 180 degree from the first line's back bearing. Okay, I repeat. The last line's forward bearing should differ by exactly 180 degree from the first line's back bearing. If not, then there is a bearing misclosure, and you need to check your data back. Okay, check one more time. Maybe your calculation is wrong. On site, Photo station can compute this automatically, however. But it's still important for you to understand this principle. And during the lab, you may need to do hand calculation. I think you just need to record down the angles that you measure. Then you have to go back and do your manual calculation to understand all the process. And then later on fill the form that I will show later. Okay. Okay, it is very important for you, every one of you, understand this principle. Okay, so you can spot when something looks off, like if your drain alignment suddenly jumps side on the drawing, you can spot it straight away. All right. Okay, next, like what I mentioned, here is the traverse reduction sheet. Okay. Each row represent a traverse leg. You record the measured distance. The measured distance and your adjusted angles. Okay, and the computed bearings here. So one by one, you need to put into the table. So these three tables, here the table is you can see forward bearing, back bearing is all right down here. Then you do some calculation. Then you can get your whole circle bearing. And this is the horizontal distance that you measured on site. All right. Then you can proceed to the next step. No worries. I will go through this one slowly, step by step. Okay, so we take the same example just now. At AF, the forward bearing is 70 degree, right? So we just write 70 degrees, 0 minutes, 0 second. Then A, you have the left hand angle. Then you also key in here, or you write down. Then you do the calculation, you get the AB, like what we say, the forward bearing. Okay. Then the whole circle bearing is the same thing you put here. Then you calculate the back bearing, BA, then plus angle B, you get BC, which is the forward bearing. Then your forward bearing is here. Okay, step by step, you got all the forward bearing here and the back bearing. So you get all the bearing. Okay. And next. So far, we've adjusted our angles calculated all the bearings, and now we are ready to find the coordinate difference between each pair of traverse stations. And this step converts your measured distance and the bearing into actual movements in easting and northing. So it tells you when you go from point A to point B, how much do you move east, west, and along north and south? Okay. The formula are quite straightforward. It's just delta n equals to d times cosine theta, and delta e equals to d times sine theta, which Shen already explained previously. Okay, so this is nothing delta n, this is delta e. Okay. So if you imagine your traverse line as a hypotenuse of a right angle triangle, then the delta n and delta e are simply the other two sides. It's quite easy, right? So let's take an example. If we are surveying along a drainage line, say from point A, a control pack near a sump, to point B, which is the next sump 50 meter upstream. And our bearing is 67 degree. Then we can compute exactly how far we've moved north and east. That gives us a coordinate shift. And once we have delta n and delta e for all the legs, we can start summing them up to check if our traverse close properly or not. So this slide give us another example, right? So of course, here is another example of calculating the coordinates difference. I think it's quite clear in the slide. I'm not going to going into the detail. You just follow the formula. You can get. You should be able to get the correct answer, right? Okay. So now let's calculate the coordinates difference and the misclosure. So since closed traverse starts and finish at the same point, the sigma delta E should equals to 0, and the sigma delta N should equals to 0 as well. Means the sum of the delta E and delta N should be all 0. But owing on-site measurement errors, there's always a misclosure. It won't be 100% accurate one. So the misclosure in easting, we call it EE, and misclosure in northing, we call it EN, right? Then a linear misclosure, E should equal to the sum of the square of EE and the EN, and then you square root, okay? So a measure of the accuracy of the traverse is given by dividing the parameter sigma d, means all the sum of all the distance among the points by the linear misclosure. So the formula will be accuracy equals to 1 in sigma d divided by linear misclosure E. Okay. So after you fill in the measured horizontal distance, and also the calculated delta E and N, you can calculate the linear mean closure. All right, you just sum it up, you get E, you sum delta N together, you get En. Okay, then you follow the formula, you can get your linear mean closure. Okay, in this example, is 0.046 meter. So the accuracy, all right, the horizontal distance, you also take the sum, which is 514.871. So you follow the formula, you use the sum of the parameter divided by your linear mean closure, you get 1 in 11,200, which is really, really small. Okay, so it is. Okay, once we know our mean closure, we need to distribute that small error back into our traverse, like what I introduced in the previous one, previously. Okay, so that every points, the coordinates are adjusted slightly to make the traverse perfectly close. And this process is called adjustment. And one of the most common method used in the construction is called Baldwin method. Also known as the compass rule. Okay. The idea is quite simple. We assume that any small error are proportional to the length of each line between the stations. All right. So the longer line should get slightly larger corrections, and the shorter lines get smaller ones. So the correction is the correction sigma E or N is equal to the error E or error N times the length of the traverse line divided by the parameter of the traverse. Okay, so it means if the line let's say AB is longer, then they will get a bigger portion of the correction. So in this example, you see AB is relatively shorter, so their adjustment value, the error is 0.006 meter. All right. Well, line BC got a longer length, then also get a longer adjustment, which is 9 mm. All right. So it's just like adjusting a drainage alignment that's a few centimeter off. You don't shift one sum by the full amount. You nudge each segment proportionally so that everything fits nicely by the time you close the loop. And after applying this correction, your new adjusted delta E and delta N value should sum to exactly 0. So that means mathematically, your traverse now close perfectly. Okay, so this is adjustment. Of course, we have another adjustment method. It's called the equal adjustment, which is used when all your measurements are taken by a total station and your line accuracy are fairly uniform. At this situation, you can use equal adjustment. So in equal adjustment, we just distribute the total misclosure equally among all traverse legs. It's quicker and practical when you set up precision. When your setup precision is consistent. Okay. For example, if you are surveying along 100-meter boundary line with 5 traverse legs, and the total mist closure is like 0.05 meters, we can simply apply like 0.01 meter correction per leg instead of calculating proportionally. Okay, so the board width is for mixed accuracy, like when some lines are longer or shorter, on site, and the equal adjustment is for uniform accuracy, like with a total station. Okay, so after you decide your adjustment method based on the real situation, you can calculate the adjustment for the E and N. Okay, like these 2 columns shown for each of your traverse leg. Then you can add up the adjustment to your calculated delta E and delta N. Then you can get your adjusted delta E and N. Okay, quite simple, right? And finally, once our delta E and delta N are adjusted, then we can compute the final coordinates. Yes, now is the final stage. So we start with the known coordinates. Usually the first control point, let's say in this case is a station A. Then step by step, we add or subtract delta E and delta N of each leg. So in this example, for station, okay, the given station A coordinates is E equals to 350 meter, N is at a 500 meter. Okay, and your delta E is minus 7.768. So your the coordinates of the E coordinates of B is 142 0.232 meter, and your your station B north coordinate will be 500 minus the correction 85.517. You get this 414.483 meter. Okay, so subsequently for your station C, you get the same thing. Okay. So we continue this for all the stations, one after another. By the end, when you reach the final station, you should land back on our starting coordinates. Okay, easy. After all this coordination, you back to A, then you'll find, yes, it's totally the same as what you have known. All right. So in real, let's say, again, I take the drainage project as an example. This adjusted coordinates from the foundation for everything that follows, pipe alignments, some chainage, structural layout, even as built verification later on. These coordinates will be the foundation. So when you stand at a sum and see what the coordinates match perfectly on your tablet, remember, it's not just GPS magic. It's because someone did the traverse adjustment right. Okay, so to recap, we've now learned how to firstly compute coordinate difference, secondly detect misclosure, thirdly assess the accuracy, and lastly apply systematic corrections. Then you can get your final adjusted coordinates. So this is what ensure your control network is both precise and reliable. Okay. Okay. All right. Everyone. Now let's we've already mastered. I hope you mastered the traverse and the coordinates adjustment. Let's take a step back and look at the bigger picture, the control network. Okay. A control network is a framework of accuracy that every survey depends on, from a small drainage alignment to a national coordinate system. You can see here a triangulation network. Okay. Oh, sorry, something wrong with the control. Okay. Okay, so in this slide, you can see the triangulation network is made up of a series of connected triangles. So each let me show the, and each vertex or corner is a control point. Okay, and once we know the coordinates of one side, we can calculate the rest using geometry and the procedures that we gone through just now. So before total station and the GPS, the surveyors in the old times relies heavily on triangulation. Okay, they would measure one baseline accurately, then extend the web of triangles across an entire region. You can imagine the old school surveyors in 1960s setting up tripods on hilltop around Singapore, not to take selfies, but to extend the coordinate system. So in modern construction, triangulation is less common on site, but the concept still lives on in how we tie our site control traverse to higher order control points, like those from Singapore's CVE1114 coordinate system. Okay. Okay, so this slide compares a network with a traverse. A traverse at the left-hand side is usually a single chain of control points. Is quick to establish, good for linear projects like a road or drains. And a network, on the other hand, consists of many interlocking connections. So every point is measured from multiple directions. And the redundancy make it more accurate and more reliable. In a building project covering multiple blocks, let's assume, we might have several traverse loops around each building zone, okay, all tied together into one larger network that ensure consistencies. So that when two construction team work on different sections on the same building site, their coordinates still match perfectly when they connect. Otherwise, just imagine, let's say, one BTO project, one block supposed to be here, but if one team take the coordinates wrong, or the traverse is not perfectly set up, then the whole block may shift. or the shape of the block may be different with the design. Okay, now let's talk about hierarchy. How control networks are built in layers. At the top level, we have the primary control network. These are high precision points established by national authorities like SLA in Singapore. They use GNSS or precise leveling to set these points with a millimeter accuracy. And these primary control points act like the anchors of the country's coordination system. You will find some of them on hilltops or roadside or inside some secured compounds. When we start a large slot project, for example, we always tie our local traverse to at least one primary control point that ensure our site coordinates align with the national mapping. So our as-built drawing don't float on the map. And in the end, it is correct. Okay, next, we establish secondary control. A denser network built from those primary points. So in this slide, on this map, you can see the blue dots are the primary control, and the red dots, which are closer, more dense, are the secondary control points. Secondary control points are closer to your actual work site. Maybe set up along the project boundary or at each drainage section or each block corner. So they are less accurate than the primary one, but still precise enough for all the construction level surveying. All right, don't worry, it's not like 100 mm difference. It won't be going like that. Okay. Okay, so here is a great example. The China Tunnel project between the UK and France in the 1980s. The engineers built two separate tunnels network from opposite side of the channel. When they met in the middle, the horizontal error was less than 30 centimeters after digging more than 20 kilometers each. So you can see how small the error is. That's the power of a well-designed control network. Layers of primary and the secondary control, each checked and adjusted until the entire system fits perfectly. So in Singapore, we apply the same principle. Just at a smaller scale, for let's say slot stabilization or retaining walls or drainage improvement or BTO projects. Our survey network ensure the design coordinates match what is built, and everything ties back accurately to national data. And today, with the GNSS and the CRAN, the Singapore Satellite Reference Network, we can establish control networks faster and with higher accuracy. But the fundamentals you've just learned, the traversing, bearing, coordinate adjustments are still essential today. All right? Because instruments can only give you numbers. is your understanding of geometry and error control that ensures those numbers actually make sense. When you are standing under the sun, holding a prism pole in Uncle Deep drain water, and your total station says the coordinates is off by 0.03 meter, you'll know exactly why and how you fix it after you understand fully today's lecture. All right. So surveying is not just pressing buttons on the total station. It's actually thinking in coordinates. So to wrap up today's lecture, we've gone from understanding coordinates to establishing traverse, to adjust for errors, and finally to connecting our network into a control network. So in short, surveying is all about travel control and consistency. Whether you are setting out a new drain, you're checking a slope, or verifying as-built data, these principles make sure everything lines up exactly where it should. And finally, please remember, when your design, your total station, and your as-built drawing all in the same page, that's when you know you've done a professional surveyor's job. Okay, so thank you all for staying with me through this session. In your next practical, you will get to apply some of these concepts in the field in your next week lab. All right, don't worry, we'll be around to get you. And I promise it will be more fun than just sitting in front of coordinates. You will try. All right, so with that, I will end today's lecture. Any questions?